Our next speaker is Dániel Prokaj from University of North Texas. And he'll talk about the continuous piecewise affine iterated function systems on the line. So please.
Thank you very much for that nice introduction and inviting me to give a talk on this seminar. So today I'm going to talk about continuous piecewise affine iterated function systems, which means I'm going to show you theorems about systems that looks like you figure on the right on this diagram. On the left, you see a self-similar iterated function system, one of the most deeply investigated objects in the field of fractal geometry. You know a lot of things about these kind of iterated function systems. Pretty easy to define such an IFS. Each function is a similarity, which means that they have a constant slope and some translation parameter. Now, the change we need to make a step forward and define a continuous piecewise affine one is very simple. We just broke the slopes of these functions. That's how we obtain such an iterated function system. One interesting aspect of this system is that, so you can tell some of the functions are not necessarily injected. We might have non-injected functions in the system as well, which is quite uncommon in iterative function systems to deal with such phenomena. The main theorem I'm going to talk about is this result here. For a packing dimension typical continuous piecewise affine iterated function system, together with Aaron Schumann and Peter Wright, we proved that we have the following nice dimension quality. The Hausdorff and both dimensions of the attractor of such a system is equal to the minimum of 1, and this dimension here, which you can think about as the similar dimension, the generalization of the similar dimension that I'm about to define in a couple of minutes. When I say packing dimension typical, what I mean is that the packing dimension of the set of parameters for which the statement does not hold is so small it has less than 4 packing dimensions. So it's small in the packing dimension sense, the set of exceptional parameters. So first, let me introduce some concepts. The iterated function system, as you all know, is a finite list of strict contractions. My iterated function systems are always defined on the real line. The attractor of the IFS is the unique non-empty compact set that satisfies this equality here in the middle. Hutchison proved that this set uniquely exists. It's a non-empty compact set, and by iterating this formula, one obtains this bit more general form of the same equality. Now, for us, this form is much more important, seeing that the attractor is equal to the union of copies of itself on the images of iterated functions, because I will use those images as a cover of the attractor. We can do that. We can reobtain the attractor with the help of iterating the functions and applying the iterated functions on an interval I here up here. So let I be the smallest non-empty compact interval whose image is contained itself. Then I iterate the functions on this interval. With that iteration, can we obtain the attractor, which means that these intervals that I call the cylinder intervals form a natural cover of the attractor. Using this cover, I define a pressure function that we call the natural pressure function of the system, simply because this cover is quite natural choice. We just take the cylinder intervals, calculate the length, raise it to the nth power, sum it up for all n-length verge, and define a pressure function the usual way. This pressure function was already studied by Barrera, who called it the non-additive upper capacity topological pressure in his article. This function is actually a special case of his function that was defined in an even more general setup. This function has the unique zero, which we call the natural dimension of the system. This is the SF that already appeared in my my formula in the main theorem. So this pressure function is trickle decreasing. It's positive at 0, and it goes to minus infinity. That's how we know that unique 0, well, that it has a root 0, which we can define the dimension with, and this number uniquely exists. Borrero also showed that this number, about the minimum of 1 and this dimension as f, is actually an upper bound on the uppermost dimension of the attractor and also on the Hausdorff dimension of the attractor. Question is quite natural. Under what condition do we have an equality here? How can we, well, force these dimensions to be equal? What does it mean to have equal dimensions up there in the formula? It is quite easy to see that the Hausdorff dimension is strictly smaller than this value if we have some identical cylinder intervals in the construction, if we have some exact overlaps. So we surely need some separation condition to make sure that we have equality here. Here I define and warming up the two most well-known separation conditions. We say that an IFS satisfies the strong separation property if for any two different words I and j that are different, the intersection of the images of fi and fj of the attractor has no intersection. That's the strong separation property, and we say that the IFS satisfies the open set condition, which is a bit milder separation condition. If we can find an open set U invariant under all the functions, so all the functions map the set inside itself, such that for different I and j characters, fi and fj, these two images on this open set U has no intersection. Well, both of these separation conditions guarantee that the Hausdorff dimension is equal to the natural dimension. But we can do more. And work with a milder separation condition called the exponential separation condition. But to define that, first I need to talk about self-similar iterated function systems a bit more. If our IFS is self-similar, so all the functions are in this form, they are defined with a slope and a translation parameter, then it's a self-similar IFS. And in this case, it's quite simple to calculate the pressure function simply because the length of the cylinders are just product of these slopes. So you've got a quite simple formula. By my definition, the natural dimension is the unique zero of this function. And we obtain that this unique zero is actually the unique SF number satisfying this yellow formula down here, which is how the similar dimension is usually defined. So the natural dimension is just the generalization, a straightforward generalization of the similar dimension to piecewise affine systems. When the system is self-similar, we can define this very mild, very nice separation condition called the exponential separation condition, or just ESC for short. First, I define the distance of two similarities, G1 and G2. Their distance is just the difference of their translation parameters if they have the same slope. If they have different slopes, we just set the distance to be infinite. They are infinitely far away from each other, so we do not care about similarities with different slopes. We only want to make sure things are separated in case we have identical slopes. Then, using this distance, we can define the exponential separation condition. We say that our IFS satisfies this condition if we can find a constancy and a strictly increasing sequence of numbers such that when we pick any number from the sequence, an NL number, On that level, picking any two words that are different, the distance of the two functions defined by the chosen words must be larger than this constant to the power n now. That's why it's exponentially separated. They're separated in this fashion on all different scales, infinitely many scales. Hoffman proved that for any self-aligned IFS on the line that satisfies the ESC, the Hausdorff dimension of the vector is equal to the minimum of 1, and the similarity dimension, which is the natural dimension. This is the result we managed to extend to continuous piecewise affine iterated function systems. And to do that, we had to introduce Markov diagrams, which is actually similar to graph-directed construction that let us track the structure of the fractals and prove results like dimension equality. So now let me introduce Markov diagrams. First, to do that, I'll need some notation. So this is how a piecewise affine iterated function system looks like. All the functions have affine pieces. Only requirement is that they are continuous, so they do meet in these breaking points in the middle. I will always write tau for the translation parameters of these functions. So basically their value at 0. I write little b's for the points where the slope changes. These are the breaking points of the functions. And I write rows for the slopes of the function, the changing slopes. Yes?
Excuse me, just let me make a remark. Because
yes.
You see that this is generally here on this picture, the images are disjoint, but we do not assume disjoint. So we allow overlaps.
Yes, of course.
But just it is drawn in this way to have a better chance to explain. Sorry.
Yeah, thank you for the comment. Indeed, it's important to emphasize that in this picture to make sure that everything is readable. These functions have disjoint images, but in fact, we do not assume any separation of that sort. The images of the interval or the attractor on these functions can overlap, of course, also the fashions. We will assume a sort of exponential separation, which is defined for self-similar sets, not for piecewise affine iterated function systems. So I will show you how we do that, but that's the only separation we'll need. The first cylinders of the image of this interval here, which is the support of the attractor, actually can overlap. And again, even on this example, one of the functions is non-injective, which is again not really a problem. Having a non-injective function in there or generates some overlaps, right? Which is uncommon. Okay, so these are my notations. This letter L will be important because it defines the size of the parameter space, right? This is the number of all the breaking points, basically. Okay. So using the notation I just showed you, now I'll define a Markov diagram. First, let me call ik the image of the supporting interval I under the function fk, and this calligraphic I will stand for the union of all these little intervals. Now I define an expanding multi-valued mapping T the following way. I pick a point y and I assign a set, not just points, but set, the set of all x's which are mapped to this y by one of the mappings. And I generate different sets with all the different mappings I have in the system. So it's not the union of all the pre-images. I take the pre-image of this y by f1, then I take the pre-image by f2, and so on, and I put them in different sets. It's important because we want to keep track of all the different pre-images. Another notation, again.
Piecewise union or some pre-image set?
It's not an union, it's a set of the privileges. So it's a set of sets. Yeah, I know. That's the bit confusing part. It's a set of sets. Yes. I know it's a bit confusing this way because it seems like an union can do the same thing, but it actually can't. I want to make sure I know that I'm not just following which function is being used, but also which affine piece of the function is being used. That's why I define these smaller, well, these little pieces f, k, j, which is just the affine piece of fk over one of its monotonistic intervals j. Now these functions are not just piecewise affine, they are nice linear, nice affine functions. These fkj, we can define their local inverses over some small intervals. I will refer to them as the branches of my multi-valued mapping T. And one more thing I need to define before I show you some simplifying diagram that will put everything in its place, which is the set of the critical points. My critical points are, well, it's a set of, well, the union of three different sets. I call a point critical point if it's the end point of one of the first cylinders. For simplification, I just assume that the supporting interval is the 0-1 interval, so we don't need even more notation for those endpoints. Those are some critical points, so the endpoints of the first cylinders. Then we take the images of the breaking points in all sort of fashion. I take the image of all the breaking points by the function fk, and then I do it with all the different fk functions. And there's one more set, this long one in green, which is just the set of points where the graph of different branches overlap and they cross each other. I also put those points into the set of critical points. So this is what's happening. I start with a continuous piecewise affine iterated function system. Looks very similar to the function I showed on the first slide. We have some non-injective function generating some uncanny overlaps by itself. We have some functions overlapping with each other. We have all sort of things happening, positive slopes, negative slopes. Then I want to work with the expansive mapping. So I flip it to obtain this figure. And I look at the local inverses of these small affine pieces of the functions. This is the multi-valued mapping T. This is how it works. These are all the branches that define this function. I take some interval. And take some interval z, let's say this little line segment, and the image of this little interval under the mapping is this interval and that other interval. Not the union of those two intervals, okay? It's not the whole line segment. It's a set containing these two intervals separately, okay? So this is how we think of this mapping T. And you can see the critical points colored on the x-axis according to this coloring scheme I showed on the previous slide. So yellow critical points are these endpoints, actually. Just when you flip it, they come to the x-axis, right? Those are the yellow ones. The images of the breaking points are the orange ones. And I have two functions where they're crossing graphs, so I also have a green one in this example. And of course, it might happen that these points are not different. A point can be yellow and green and orange at the same time. It's not a problem. I just want to make sure that all these different points are in the set of critical points. Okay. So we have this union of intervals calligraphic I. Again, calligraphic I, want to use this figure once again, is the union of these two line segments on this example, right? So we just get rid of the gap between it, basically. That's what we do. That's why I had to define this other set. and we partition it with the help of the critical points. And the elements of this partition are called the monotonicity intervals, where all the functions are nice and monotonous over these intervals. That is, about these intervals, the monotonicity intervals, the expansive mapping T is always linear, and the branches can only take the same value at the boundary. Now, that's why I defined a set of critical points the way I did, to make sure that they can all take the same value at the boundary of these intervals. So I have this expansive mapping, but I still don't have a Markov diagram. I have to define something called the successor of an interval. So let's pick a monotonicity interval, the C interval again. Its endpoints are the critical points, some critical points. We introduce an arrow from C to D, and we say that this set D is the successor of Z if D can be obtained as an intersection of one of the images of Z by T and one of the monotonicity intervals. So that's the idea. The image of Z was again the set containing these two intervals. I take an element from this image, one of them, and intersect it with the monotonicity intervals, and that's how I define a success. That's how I define a successor. We can also keep track of the branch that was used to obtain the successor. And I write omega z for the set of successors. Okay. So this set is the set of all the little intervals that can be obtained by the intersection of one image by T and one monotonicity interval. Now that we have a multi-valued mapping T and the successors, I can finally define the Markov diagram following Hopper and Wright, who defined it for expansive systems. For piecewise monotonic expansive systems, we say that the set equipped with this arrow operator is the Markov diagram of f with respect to the monotonicity partition Z, not if D is the smallest set containing this partition that is close to making successors. So we start with these monotonicity partitions, generate all the successors, put them in a set, then we take the successors of the successors, put them in a set, and so on. The successor of everybody is inside the set itself. That's how we define it. And of course, we cannot guarantee that this set is finite. It can be finite. Similarly, we can define the Markov diagram using any finite partition, not just the monotonicity partition started with. It does not really have a special role in the sense of defining the Markov diagram or building it up, but the diagrams I want to use in the calculations, I'll start with the monotonicity partition for a refined. Okay, so the Markov diagram actually looks like a graph, a large graph, potentially finitely large directed graph, whose vertices are the little intervals I generated. Between two intervals C and D, we have a directed edge in the diagram, if and only if, so we have an edge from C to D, if and only if D is a successor of C. So when we walk in this diagram, we are actually moving from one interval to another one, which is a successor of it. We call the Markov diagram irreducible. There exists a directed path between any two intervals as such. So sure, starting from the monotonicity intervals can walk up to their successors, but we must be able to walk back to any other monotonicity interval as well if the diagram is irreducible. And actually, this is the reason why we need the continuity in my definition of this system. That's why I have continuous piecewise affine systems, because when the functions are continuous, we don't have to assume that diagram is irreducible. It will be irreducible all the time, simply because of the continuity. If they are not continuous, it can happen that the diagram is not irreducible, and we have to assume that it is. I have a diagram, and I want to define a matrix that will help us calculate the dimension. In an analogous way to graph-directed iterative function systems, actually, we define this matrix F indexed by the elements of the diagram D. Following way, we take all the arrows from C to D with different branches, and we sum up the derivative, the absolute value of the derivative of the corresponding branch to the raised to the power S. Then we sum it up for all different branches that can send C to D to calculate the C, D entry of the matrix, and we write zero otherwise. If there are no branches sending C to D, then the value in the matrix entry is just zero. Simple. So this matrix is often associated to something like graph-directed iterative function systems. And when the diagram is finite, then our system is actually a graph-directed iterative function system. So it's quite easy to deal with that situation. We already know a lot of theorems about those systems. Let C be a sub-diagram of D, and we write EC for the set of ECN for the set of n-length directed paths in the subgraph defined by this C. Let's assume that it's irreducible. Then I can define the pressure on the subset similarly as I did for the function for the whole diagram, actually, simply by restricting the set of words I can use in the summation. So the definition is the same, but I sum for, well, not for all the intervals, but only a subset of them defined by this sub-diagram. We need these sub-diagrams because I actually want to calculate the dimension by approximating the full diagram matrix with subsystems, with finite subsystems. That's the idea. It's important to know that as an operator, this infinite large matrix F, which can be an operator again, power n is always bounded in the subnorm. So we can define its spectral radius with the help of this limit. This limit exists. We can define the spectral radius. And now that we have a spectral radius, something we can compute, we can use it to calculate the natural pressure at different S values. If the sub-diagram C is irreducible, if it's irreducible, we know that the pressure is upper bounded by the logarithm of the spectral radius of the matrix of this sub-diagram. If we know more, namely that it's not just irreducible but also finite, then these two values are equal. So we need finiteness to make sure we have equality, but it's always an upper bound. So we can work with it. Now, I'm about to show you how the matrix theorem is being proved using the Markov diagrams and the properties, relying, well, on several other theorems as well, but mainly on the lemma I just showed that connects the spectral radius with the natural pressure function. So again, this is the main theorem that I'm about to prove you. Of course, I've completed. I just want to show you the main idea of the proof and how Markov diagrams are used to prove such a result. So I want to obtain this equality of dimensions for typical parameters. And again, this is how I parameterize the system. Rho stands for the slope, tau stands for the translation parameters, and I write P for the breaking points. Okay. Now I can show you a formal definition of the pattern dimension typicality. We fix a type, a vector that has the number of breaking points of all different functions as its coordinates, and a vector of contractions, a vector of all the row slopes. Can be positive or negative, strictly less than 1 because we have contractions, and we only assume that it's non-zero. And of course, the dimension of this vector is L, the number of breaking points plus 10 because we have an extra slope. You start with the breaking points to count them. Let P be a property that makes sense for every piecewise affine system, and consider the exceptional set of parameters of breaking points and tau parameters, such that the corresponding piecewise affine system does not have this property P. So it's an exceptional set, a set of all the exceptions. We say that this property holds packing dimension typically if for all type vectors and all contraction vectors rho, the packing dimension of this exceptional set is strictly less than L plus m, which is the dimension of the full space that it exists. Okay, so this is how we define rigorous packing dimension. Difficulty has strictly less than full packing dimension. I want to use the exponential separation condition, but it's defined for self-similar systems. So I need the generated self-similar IFS of this continuous piecewise affine construction. I have these piecewise affine systems, and for all the different affine pieces, all these line segments, I define a similarity, a nice line defined over the whole real line. So they continue outside of the bounds of this graph as well. They are defined on the whole line. This is what I call the generated self-similar IFS of this piecewise affine system. They fix the vector of slopes. And for fixed vector of slopes, there is a non-single linear transformation depending only on the slopes that sends these the horizontal and vertical translation parameters of the piecewise affine systems, the taus and the breaking points, into the translation parameters of the generated self-similar system. So this T vector has the vertical translations of the self-similar matrix in the generated IFS. We have this nice connection with this non-single linear transformation, which means that we can calculate the dimension of the exceptional sets and send it to the set of the other space with these parameters. And we can work with the linear functions, which what we want to do, because Hoffman proved that the packing dimension of these parameters, the exceptional parameters of the generated self-similar IFS, must be m minus 1, so strictly less than 4. We know that dimension, which means we also know that if the EST is assumed, we have less than 4 packing dimension in the original parameter space. What we proved is the following. Let us be a continuous piecewise affine iterated function system with generated self-similar system S, and assume that S, the generated self-similar system, satisfies the exponential separation condition. Then we have this dimension equality. That's what we had to prove, because if you can show this, then by Hoffman you know that this property holds packing dimension typically. To prove this, we need to approximate the Markov diagram of this piecewise affine iterated function system with finite subdiagrams. And then we will rely on Senator's result. According to Senator's result, it can be done if the piecewise affine system has, well, one other property, because irreducibility itself is not really enough. We need the existence of certain eigenvectors. Unfortunately, it's not a condition. We say that the system is linearly reducible if, for some refinement of the monotonicity partition, the corresponding matrix that I assign to the Markov diagram has left and right eigenvectors with non-negative entries for the spectral radius as an eigenvalue. We need to guarantee that we have these eigenvectors, and then we can do the approximation of the spectral radius. That's why we need this property. We need to assume that a system has limited reducibility. And since it may not work for every single Markov diagram we generate with some active partition, the partition for which it works will be called the limiter reducible partition, the corresponding diagram, the limiter reducible Markov diagram, and so on. The following proposition is actually the most important idea in the proof. If we have limited reducibility, then the spectral radius of the matrix of the original diagram has its spectral radius. It can be approximated with the spectral radius of a subsystem, finite subsystem. For any epsilon, I can find a subsystem that approximates it by more than epsilon. That's the main idea of this proposition, which uses limited reducibility. Now, using this proposition, some other lemmas, we can finally prove that, well, this theorem which stated that if we have exponential separation condition, then we have dimensionality. So we know that the natural dimension is an upper bound on the Hausdorff dimension. It always holds, so we only need to prove the other direction. Let's choose an arbitrary t-value less than the natural dimension. And by the lemma I showed you, we know that since we have irreducibility, the pressure at this value t, the pressure function, is always less than the logarithm of the spectral radius of the corresponding matrix. Now, according to the proposition, we can find a finite subsystem whose spectral radius logarithm is equal to its pressure because it's finite and irreducible. And I can choose this C such that it's arbitrarily close to the original one, right? We can approximate it because we have limited irreducibility. Now, since this C subdiagram is finite, we could use a theorem proof with Kyle Shimon that works for graph-directed iterated function systems. If the generated self-similar IFS S of the continuous piecewise affine system satisfies the EFC, then the Hausdorff dimension of the attractor is equal to the minimum of 1 and the natural dimension of the system. We proved it for self-similar graph-directed iterated function systems, and the C sub-diagram I'm using in the approximation is finite. So it defines a graph-directed system, so we have to know that it has the dimension equality. Since it has dimension equality, doing, well, a very short case analysis because we need a minimum of 1 in the natural dimension, but it won't really make things too complicated. As you can see, just an extra line actually in the proof. If you know that it's less than 1, so this should be the value of the minimum, and the minimum of 1 in the dimension is the dimension itself, then since we know that the pressure is bigger than 0 at any values that I could choose, and it's less than the natural dimension, I will have this nice approximation, and it will yield that the Hausdorff dimension is actually larger than or equal to the natural dimension, meaning that it must be if we have exponential separation and limited reducibility. Now that's the property I have to talk about a little more, but don't worry. It looks like it's an extra requirement we need, some very technical requirement, but in fact, we don't have to assume it because it's granted by the exponential separation already. To prove it, he used the following lemma of power. He showed that if you think of the associated matrix as a block matrix with these 4 blocks, P, Q, R, and S, now we only need to focus on these 2 blocks. And recall that this matrix is actually an infinitely large operator. This part is finite dimensional, finite times finite, and this one is the infinitely large block in the bottom left, actually. So these are the 2 blocks we want to focus on, we need to focus on, because if you can show that the spectral radius of the whole matrix is strictly larger than the spectral radius of this residual part that we don't want to deal with, then we have limited reducibility. Now, this very nice lemma of Hochbar helped us prove that we actually always have limited reducibility as long as we assume exponential separation. Now, this lemma always applies for systems without overlaps. That's how Hochbar used it in his paper, because he worked with expansive dynamical systems. He had no overlaps. Unfortunately, we do have overlaps, which means that in the matrix, some entries are sums of different ratios. Raised to some power s, they can be larger than 1. That's why we have to show that the lemma can still be used. To do that, we investigated the different types of overlaps we have in the system. We want to differentiate between these two types of overlaps. The one on the left is what we call the light overlap, because it's very easy to deal with these ones. The second type, the cross overlaps, when two branches overlap and they do have a common point, it was a bit harder to deal with. So first, about light overlaps, if you choose a finite refinement of the monotonicity partition, you can choose it such a way that the images of these small refined little partition elements will all be disjoint because the overlap is there. So you actually have no overlapping in the system if you start with the right refinement. You have no problem, all the matrix entries are less than 1. If you have cross overlaps, then it's a bit more complicated to deal with it. But we still have no problem because we have EFC, which implies that the crossing point where the different branches intersect, when the graph of those branches intersect, cannot have a periodic orbit. That's the only thing we need actually. That this point here, when you do the iteration and it moves around the interval, it cannot come back to itself. Okay, it moves around on the x-axis, but it cannot come back to its original position because we have exponential separation. It's a very nice consequence of exponential separation, actually. And that's what we need. That's what we needed to prove that the case of cross overlaps can also be resolved, and we don't need to require limited reducibility as a separate requirement. It follows from exponential separation. So I won't show the detailed proof because it's rather technical, but the idea is to choose a small, another refinement of the original monotonicity partition. And then you focus on the cross overlap and you choose a refinement where the partition element that has this crossing point as its endpoint is so small that when you get rid of it, you don't lose too much from the spectral radius action. You basically you forget about all the different crossing branches and all the overlapping branches. You only focus on the largest one. You dominate the system over that small little monotonicity partition from this refined partition. So not necessarily from the original one. You might need to choose a much smaller one. But then you prune all the branches that are not maximal. You only keep one. You don't have overlapping anymore. Do the calculation, and thanks to the exponential separation and the lack of periodic orbits, it can be proved that the spectral radius of that residual part from Hochbar's block matrix is less than the spectral radius of the original matrix. So we are fine. Now, at the end of my talk, I want to mention another nice result we proved with Peter Reid on these attractors. Only briefly. So we proved that for a fixed time vector and a slope vector with positive entries, for living almost every, translation parameter. I like to refer to both of these as translation parameters because the breaking points are actually horizontal translations of this system, of these functions, and the tau parameters are the vertical translations. So for living almost every breaking points and tau parameters, we know that if the natural dimension is strictly larger than 1, then the Lebesgue measure of the attractor is positive. So we also have this nice result on the Lebesgue measure of the attractor. This notation here, lambda b tau, stands for the attractor of the system defined with these translation. The proof of this result relies on a nice continuity argument, the continuity of the natural pressure function, which can be proved by showing some sort of continuity of the Markov diagrams. Continuity of such a diagram essentially means that the new system you obtain by perturbing the parameters a little bit has the same common initial component in its Markov diagram as the original one. So things start with the same couple of steps in a very similar fashion. Then we say that the Markov diagrams are close to each other. We have this sort of continuity of these objects. And using that, we can show that the pressure functions are continuous. Actually, as you can see in this lemma, it's not really continuity. Assuming we have limited reducibility, which is needed again because of the spectral radiuses that we want to approximate, we only have this last continuity actually. That's the only thing we have with the parameters. All parameters, slopes, breaking points, those are close to each other, so I only perturb the system a little bit. Then I know for sure that the new system is larger than original minus epsilon. I mean the pressure function at some s value. To guarantee that we have continuity, we need a little more. We have to assume that there are no exact overlaps, actually. And that's the only separation we need to assume. Because if you have exact overlaps, you might have some functions with a common fixed point. One of them has different slopes on both sides, on the two sides of this fixed point. And when you move it a little bit, suddenly the larger slope will take action. Previously, it didn't really do anything. It depends on your construction. You can basically force it outside of the attractor. Then you move it a little bit. Suddenly, it takes action, and the dimension jumps. And it doesn't matter how small your epsilon is, it will jump. If you started with a system with exact overlaps, but it can only happen if you have exact overlaps. There's no problem with any other types of overlaps. Only with the more vicious case. So if you assume that you started with a system that has no exact overlaps, then you have continuity of this pressure, which implies that the natural dimensions are also constant. So you can approximate it the way so. We also proved actually how large can the dimension jump when you have no exact overlaps. You need to define another matrix, a different one, not the one we associated to the Markov diagram, but one that does something similar but works with the endpoints of the monotonicity partitions instead. And with the help of the spectral radius of that matrix, you can upper bound actually the jump you experience when you move the parameters and you start seeing some problems. So we can also bound the jumps, but the important part is that we have continuity with this very, very slight extra refinement. Okay, that's all I want to tell you today about Markov diagrams. Thank you for your attention.
Thank you very much.
Thank you.
Questions, comments?
This approximating with this finite.
Yes.
Basically, it's approximating inside with the self-similar
Exactly. We looked at self-similar systems whose attractor are inside the tractor of the original one, and we are trying to flow without to get as close to the original one as possible. Yes, exactly.
My question is about the corresponding similar measures. If I understand your strategy now is approximating from inside.
Yes.
But do you have any hope to grab the dimension of similar measures? Even if it's possible to find a naive upper bound.
Oh, for the dimension of the measures?
Yeah.
We do have some, yeah. It's also possible in some cases to have this approximation. It's also doable to have a measure whose dimension, well, can be obtained actually as the supremum of the dimension or the approximating measures in some cases, but we need further assumptions to do that on the slopes actually to make sure that works. Otherwise, it's a bit more complicated in the general case. But you can do, you can use the self-similar systems that are all inside to define some, the usual self-similar measure and use them as an approximation to get the dimension. So yeah, we did that to get the but it's not trying to just.
I just like to make one more comment that this whole thing had its roots back in 2001 when I met a person, maybe a physicist, I forgot his name, and he asked me about dimensional results for the fractal of iterated function systems when the functions themselves were not injected. And I told him, no, we didn't have anything like that because all the iterated function systems I had seen all until that point. And then it stayed in my mind that Dániel came at, and this was his PhD next work. So it's basically, and also the master. So it's basically, I didn't know any other system, an iterated function system, which contains non-injective methods. That was somehow the motivation to do something.
Yes, because you want to bound the derivatives away from zero in the other as well. So if you want to have something non-injective, you really need to look at these systems. And it will be nice to use them as an some approximating method to get them.
Even though you were not injective, you were again far from being simple. So having plateaus of zero derivatives would make the life again much harder.
Yes. Yeah, this is just the first step in this direction. And, we hope that some people want to model the nature in a way that they run into the situation where they need to use methods which are non-injective, may use this, but most probably those people don't know about this design and this. So that's it.
Thank you very much. If there are no comments, questions, then let's thank Dániel.